Hello, everybody. In this video, I'm going to give you a quick application of the principal actions theorem. It's going to be only 2 pages. One will be the actual just work. The second one will be a picture, so you can see kind of what happens. And the last part of the application will be how to use this idea to graph conic sections in general. All right. So suppose we have this function. This thing here is certainly a quadratic form. And it's written currently in the standard system. So we have the normal everyday axis system that you're used to. Notice that you can write that in quadratic form this way, where the vector x is x1, x2. But then that means that that matrix that you see, 1, 2, 2, 1, is a symmetric matrix. So it's orthogonally diagonalizable. So I found an orthogonal matrix that will do that diagonalization. And also the 2 columns, when you orthogonalize them, when you normalize them, they actually have the same length. I set it up that way so that this would happen, so the computation would be too bad. They actually have the same length of the square root of 2. So I just take the square root of 2 out in front of the matrix. That makes it easier to deal with. So the diagonal matrix is just a diagonal matrix of the where the diagonal is the eigenvalues. So Q transpose times A times Q is the diagonal matrix D. Okay, so now go ahead and replace x with q times y. By the principal axis theorem, the function, but in the new system, y1, y2, would be given by the formula 3 times y1 squared minus y2 squared. And that's in the basis B, where B is the set of vectors q times e1 times q times e2. Now, usually students have a hard time understanding why and what the hell that means. So then you need to remember kind of a picture. When you say the x-axis and y-axis, you guys just think lines. Don't. Think E1 and its span. You think E2 and its span. So in a system, I need to know what that corresponds to. So in the y1 system, so in the y system, E1 makes an axis. E2 makes the axis. But that's those vectors in the y system. I want to know what they are in the standard system. So to find what they are, I remember that if you give me the vector in the y system, I can multiply to get the vector in the x system. So this is the vector that defines the y1 axis in the y system. But then that vector is actually this vector in the x system, the normal standard system that you're used to. Now, granted, when you look at this, it might be really hard to understand. So on the next slide, I'm going to do the same thing with pictures. Here we go. Same thing with pictures and with certain numbers. So we don't have quite so many symbols. There we go. We have our function. Our function currently is being written in its standard form. Its standard basis form. So that's x1 squared plus 4x1 x2 plus x2 squared. I hate that cross product term. But if you look at the point 1, 2, I plotted the point for you on the plane. I can then evaluate the function at 1, 2 to get the value of 13. Now remember how functions work. Students forget. You're associating a point with its value. What you call the point doesn't matter. You guys think it does. No, you have a point in the plane. If I had to say, all right, I'm going to call this point Bob. F of Bob is 13. Great. Someone might say, oh, don't call it Bob. I don't like that name. Someone might say, fine, I'll call the point Rose. F of Rose is 13. What we refer to the point doesn't matter. That means then the system we use to generate the coordinates doesn't matter as long as I adjust the formula. So let's do that. I'm going to change the system. I'm going to go to the y system. To do so, I'm going to use a substitution that x equals q times y. Remember now that y is y1, y2. So there's a y1 axis and there's a y2 axis. In the y system, the y1 axis is defined by E1. But to find out what that is in the x system, I'd have to find out then what is q times E1. That's the vector q1. Notice the first vector The first column of Q defines the first axis in the new system. Define the Y2 axis in that system, in the Y system. That would be the vector E2. But to find out what it is in the standard system, the X system, that vector X would then be Q times E2. That would then be the Y2 axis. Those two vectors then define number lines and around them make a graph. So then that graph is actually this thing right there. That's the new axis system. Now notice that the point didn't move, did it? So wherever the function is at that point, it's still got to be 13. But what we call the point has changed. And how we refer to, how we evaluate the function changes. But the value at every point can't. All right, let's find out then, what should that point be? Now looking at it, it looks like the Y1 coordinate is a little bit more than 2. And the Y2 coordinate is a little bit less than 1. But that's not good. I can't just guess. But we remember, though, that X equals Q times Y, and Q is invertible because it's an orthogonal matrix. And in fact, the inverse of Q is Q transpose. That means then Y has to be Q inverse times X. But that's right. That's Q transpose times X. That's a typo. It should be an X there, now Y. It's an X. That's an X. But we know what X is. It's just the vector 1, 2. And I knew what Q was, so I can take its transpose. So the vector Y has to be Q. That was 1 over the square root of 2. The transpose would then be 1, 1, negative 1, 1. And I multiply by 1, 2. If you multiply that out, you get the vector 3 over the square root of 2, which is a little bit more than 2. And 1 divided by the square root of 2, which is a little bit less than 1. Neat, right? Right? So we now have a new name for the point in this Y system. But the principal axis theorem says that I don't have to worry about what the new function should look like. I know it has to look like this. It has to be the first eigenvalue times the first variable squared, plus the next eigenvalue times the next variable squared, and so on. So it has to be 3 times y1 squared minus y2 squared. Let's just evaluate this function at the point using its new name, which is 3 divided by the square root of 2 and 1 divided by the square root of 2. By just plugging in those numbers, notice you get the same answer because you have to. Because the function is associated with the point, is evaluated at the point. The numbers, what you call it, doesn't matter. The numbers depend upon the system we use. All right, good. And I believe that's enough of that one. After this, we now go on to tackle how to use this idea to graph conic sections that have cross product terms.